Well, that is the okay, so you're saying that's the similarity. Okay, so like everything under the sun bonds by using its valence electrons because its inner core electrons, they're pretty stuck. They're notably more attracted to the nucleus than the valence electrons are. So how does an ionic bond form? Something from this table, mirror this table. How does an ionic bond form?
Because like there's a bunch of electrons floating around, so the cat has to figure out
So let me come back to you guys. You just grab metallic. Brandon's group, tell me how an ionic bond forms.
the non-metal metal that have like close valence electrons combined with and one of them.
Still not 100%, but closer. Syrian's area. Actually, how about you guys go ahead, compare, contrast ionic, metallic, and covalent. Go. You guys need to talk about this right now. Talk. Stop doing your lab homework and talk about this.
Ionic is when one like holds the atomic electrons on the like 6 and then with valence when they share electrons.
All right, come back to me. 5, 4, 3, 2, 1. Okay, I know it's a sleepy Monday morning, but I'm trying to jog your memory of things. We have a 25-ish minute quiz tomorrow. It's a big quiz, but not a test. It's a quest, is like I like to call it. And it's all the content that we've learned so far with bonding, which is not really all that much, but it's mainly comparing and contrasting everything in terms of metallic, ionic, and covalent. So ionics transfer 1 electron, 2 electrons, 3 electrons. That's about it, because they usually have 1, 2, or 3. Metals usually have 1, 2, or 3 valence electrons. So they're transferring a small number of electrons. Done. It's transferred. There's a negative ion, there's a positive ion, and then what do? Negative ion, positive ion. They just kind of hang out near each other because they're attracted to each other, and so that builds and builds and builds and builds, and it makes this nice lattice structure. That is just a single metal and non-metal, or maybe 2 or 3, depending on how many are actually coming together. Covalent bonding, they literally share. They throw 2 electrons in the middle of them. They go, okay, we're sharing. This is called a covalent bond. Sometimes it's a polar covalent, sometimes it's a non-polar covalent, but still, they're still sharing. Then we get this crazy metallic bonding situation where it's not just one cation or one metal. They actually, a bunch of them come together. They all dump their valence electrons in this big pool, this big vat. And as they kind of float around each other, there's this continual, I'll show you the picture first and I'll come back to this. As they dump their electrons into this big vat, there's a lot of attractions that can occur in the sea like ocean, of delocalized, meaning electrons are delocalized, not in one place. Sea of delocalized electrons. So if you need a diagram that out for yourself, draw a blob. Okay, blob has been achieved. You have your cations in the middle, kind of just floating around, and there's the electrons are just floating all the way around everywhere else in a sea of delocalized electrons. So if there were a specific ratio of the cation to the electron, you can see that silver, Ag, forms a 1+ charge. How many valence electrons did it lose? Shut it out. 1 valence electron. But if I put, let's say, calcium in here, what charge? Look at calcium in the periodic table. You guys have a blue one in front of you as well. Look at calcium. How many valence electrons does it have? 2. So what charge would it form? Say again? +2, because it will lose those 2 valence electrons. So for every 1 calcium atom floating in our sea, you'll have 2 electrons kind of nearby. Whereas for the silver, you only had 1 valence electron nearby. Yeah.
Some like some elements towards the middle, like iron, they tend to be like magnetic, and they have more valence electrons like on one side and then more positive.
Magnetic nature comes from the pairing of electrons, actually. So if you have an orbital with all your electrons paired, you're not going to respond to a magnetic pool or magnetic field. But if you have one of your electrons not paired, that's when you act magnetic, because you have an electron spinning one way and it's not being countered by an opposite spinning electron. Kind of a different story, so not related to this, but a good question. Okay, So that's how our metallic bonding looks like, right? And so we call it an interparticle attraction because it's between two particles. One particle is the cation, the positive thing. One particle is the electron, the negative thing, and so there's an attraction there. So it's kind of like ionic in the fact that it's just an attraction, but it forms totally differently. So different examples of metals or metallic bonding situations are alloys. Who's ever heard of an alloy? Everybody's hand goes up, okay? Can anybody give me an example of an alloy? Steel, okay, say again. Titanium what? I heard steel. You guys find steel on the periodic table. Oh, dang, I was hoping I could trick somebody. Okay, I saw a couple heads go up there, but no, it's not on the periodic table because it's not an element. It's a blend. So a blend of two or more different metals gives us an alloy. What is a steel a blend of? Carbon and iron. Okay, we'll talk about why it's that way shortly. Anybody else have another example? Say again? Bronze, okay. So can you guys find bronze on the periodic table? Okay, so bronze will be a mixture of some other metals. All right, so, and then here's the premise of how it actually bonds together. I mean, how the bonding process occurs. So we're talking about the valence electrons becoming free, floating around. They're called delocalized because they're not in one place, right? So they can float around, and that gives them a lot of properties that metals have. So I need you guys to shout out 3 properties that metals have. Go. Malleability. What else? Ductile and conductive. And they're conductive, which is a special one. That is, it's conductive for electrical and heat. Electric and heat, or thermal energy. Yeah, so it is conductive in both of those respects, but it's conductive in a state that ionic is not conductive. Say again? Solid. It is basically conductive in solid and liquid form, whereas ionic compounds, are they conductive in this form? No, because the electrons are stuck and they can't move, they can't create electrical flow. Whereas metallic bonding, the way it forms its bonds, does allow that for it to occur. So basically, the way it forms its bond creates all these fancy features that other things cannot have. That's what the rest of these notes are kind of about. We'll talk about alloys, remember a lot. Okay, so explain why metals are conductive. This basically means that you know what conductive, what is it? Like, what is it? How does it happen? So conductive means that electrons can flow. That's all it means. So if your electrons are flowy or have the ability to delocalize themselves and bounce around, they can be conductive. So motion of electrons carries electrical charge or thermal energy. That's basically what an electron can do. And so in a metal, because it's got a sea of delocalized electrons, it can do that. Can it do that in a covalent bond? Are covalents conductive? No, they're stuck between 2 atoms. They cannot move. When can an ionic be conductive? Aqueous, or what's the word for liquid? Think lava? Molten, right? It can only do that whenever the electrons are free to move. All right, so malleable and ductile. What's malleable actually mean? Flatten into a sheet, okay. And what does ductile mean? Yes, you can pull it into a wire. So basically, both of these are physical changes that take a shape, like let's say we had I don't have a piece of ore up here, like a big rock with a bunch of metal in it. You could flatten it out, and you could flatten it into a thin sheet. Think of like aluminum foil. That's flattened out aluminum. Or draw it into a wire. What makes a really good wire? What's very conductive? Copper. Copper makes a great wire. So how do they do this? Basically, normally when you start to pull stuff apart and flatten, it starts to break. It crumbles and breaks. That wouldn't be ideal if we wanted to, make a big sheet of metal, or to make a wire that was 10 feet long and if it broke up, we wouldn't have any kind of ability to conduct electricity. So basically, the electrons fill the gaps and create a cohesive surface because they're mobile, all going back to the mobile electrons, all going back to the delocalized electrons. As you start to flatten something out and pull it into a wire, the electrons start to kind of fill in the gaps so there's no breaking occurring or cracks. And so along with the electrons, what's attracted to those electrons? What's inside here that's attracted to those electrons? The cations that the metals are kind of just, they become. So along with those electrons that are filling the gaps, also comes the cations, which fill in more of the gaps, or kind of just come along with the electrons to create a cohesive, kind of continuous flattened surface. So it's nice to be able to explain why that happens based on the premise of how the metallic bond forms. And another word that you can use to describe ionic electrons, we've been saying localized because we're saying basically delocalized. And we can say that they're non-mobile. The word static also means that, if you're looking for some more words to kind of relate or compare and contrast the bonding types. All right, so raise your hand if you are wearing some form of jewelry or something metallic. Okay, a couple of us, okay. So I used to play the baritone in 8th grade, and I'd carry my huge instrument box from the middle school to the high school where my mom worked. And my grandpa gave me this ring, and like after a week of carrying that dang huge box, my ring was bent. Why? Well, I mean, why doesn't the plastic of the handle bend of the instrument box? Well, I heard because it's plastic. Yeah. Can you tell me more then? Why was my ring bending and the plastic wasn't? Yeah, William. But I was holding it like this, right? So it's basically opposite and equal forces. One was going up because I was holding my hand up, and the instrument's going down. Yeah. Yes, we're looking at the properties of metals, right? It was able to bend because it was a metallic ring, or it was a let's say 24 karat gold. So if you were trying to buy somebody some jewelry at some point in time in your life, would you guys choose to buy like 12 karat gold, 14 karat gold, or like 24 karat gold? Well, gold can be white gold. It's still going to be a version of gold. What would you guys say? Why 24? Because what? It's a big number. But what does that actually mean? Okay, so it relates to the percentage of actual gold in it. Okay, you guys have seen the Olympic medals. They put it in their mouth and then they do what? Bite it, and what happens? Why does it bend? Okay, so do you think if you were buying somebody a piece of jewelry, they want that metal to just bend all the time? No. So do you think you'd buy them something that was high percentage pure gold or low percentage pure gold if you want it to last? Why low percentage? Ooh, you said other stuff in it. What is he basically saying we have? An alloy. Okay, so guys, girls, whoever you're buying for, tell them they need to learn the chemistry behind what they are getting so they understand why you went cheap and got the not so expensive 12 karat gold, 10 karat gold. Like, honey, it's going to last forever, okay? None of this, hold on, let me come back to this. None of this 24 karat gold stuff, okay? So, basically gold is made up of these three things. Silver, copper, gold, maybe a little titanium, maybe a little platinum. It kind of depends on what other blends come into play. Why in the heck are they calling it gold? Okay, because it's like, oh my god, it's gold, guys. Yeah, so it's got gold in it, right? It's not like, oh my gosh, she got me a silver ring. Ah, no, there's nothing of that. It's like, he got me a gold ring. Okay, that's why it's in the Christmas song. 5 golden rings. Okay, thanks, guys. Appreciate you joining me there. So, and it's actually an alloy of numerous metals. So why would we want all these metals in our alloy? Okay, so they add what? What'd you say? They add strength. They add some sort of desired characteristic. And some of those desired characteristics can be things like non-reactive. I hope you're writing down like the premise of why an alloy is forming, not just me. It's me and my board. Okay, so they add strength, they add some sort of desired characteristic, and those desired characteristics can be somehow limiting the reactivity. I'm sure you guys have seen those backs of like jewelry labels like contains nickel. Why does that matter? Does anybody know why that matters? No. Okay, so it shows not pure, but also sometimes things that are pure metals, they react with your skin. Who's ever maybe seen somebody have like a green ring around their finger or their ears, like turn slightly green, or their neck from a necklace? Different impure or different metals react with your skin, and they deposit ions on your skin. Well, nickel happens to be green in its ion form, and copper is blue in its ion form. Iron is greenish blue and yellow green, and two of its ion form. So it basically turns your skin colors. Like, no, you don't want that. So they somehow, whenever they add their alloys, it's going to make them non-reactive with your skin, which would be desirable so you don't come out like tie-dyed after you put your ring on. Some other characteristics are they have a high specific heat, or specific heat capacity, which means that they can hold heat really, really, really well. Well, back in, 1800s or so, why would they want some sort of metal to hold heat really well? Say again? So they built like wood fires, no, like electric grills, like, let's start the grill up, honey. No, it was like you put the logs in the fire, you warmed it up, you waited, your food got warm or cooked and so forth. And then sometimes you weren't back in time to eat that meal, so they wanted to stay warm. So instead of burning all their resources, they just kept it warm. So what kind of materials do you think that they use to keep their food warm in? Say again? What kind of metal? My mom has one. It's really, really, really heavy. Say again? Cast iron, right. So think of cast iron. So cast iron, has what metal in it? Iron. And the cast iron part of it actually has carbon in it, because carbon has a really, really high specific heat capacity compared to just iron. Iron, I don't know if you guys ever cook in the kitchen, but you put a cookie sheet in the oven, you put your little thing you do on your hand, grab it out, stick it on the stove. It cools down in a matter of a minute, because metals don't hold heat very well. They conduct electricity, they conduct heat, but they basically let all the heat out of their internal part of the bonds really quickly. So if you want something to stay warm, you have to add something else to the metal. So iron doesn't hold its heat very well, but carbon does, so it blends it to make a more desirable property. Yeah.
So that same combination makes steel like a
different ratio. Yeah, different ratio. Mm-hmm. So, and this is an example. These are your different carat weights, 24, 18, blah, blah, blah. So this one's basically almost 100% gold, whereas this one's going to be a ratio where you have, let's say 80% gold, and what else? What else did I say was in gold? So maybe 10% silver and 10% copper, something like that. So you can see how the ratio changes as we go. So does an alloy have a specific ratio? No. So back to this slide, I wanted to see what you guys would tell me first about the desirability of it. These are some of your common ones that you guys already mentioned. Cast iron. Well, see if I can scroll down my board, but I can't. So cast iron, we said carbon and iron, and then bronze is copper and tin. Who's a racing fan? Oh, nobody? Just my sister-in-law. She's like a hardcore Dale Earnhardt Jr. We're three. Okay, Dale Earnhardt, we're three. But she loves racing, and NASCAR and all things come with that. So she loves to go see the bronze statue of Dale Earnhardt in Kannapolis. Have you guys ever seen it? Okay, if you have not, it's a sight to be seen. Okay, but it's actually bronze, which is it's not an element at all. But why are they choosing bronze? Because one, copper is pretty. It's one of the only colorful metals that have like that sheen of a different color than just silverish. And so in the tin in it also creates a little bit of color, but it also makes it stronger. Because I don't know if you guys know, what's the Statue of Liberty made out of?
Copper.
Copper. But what color is it? Why not copper? Why did it change colors? It oxidized, okay, but why did it change colors? What's that green stuff called? Nobody knows. Patina. Write this down. Patina is copper oxide layer on the Statue of Liberty. I'll make a fun fact sheet for us sometime. Okay, so it is, yes, it is copper, but it's now a reactive form of copper, which is copper oxide, and it's called patina. It's that flaky kind of green, mossy looking stuff that flakes off of the Statue of Liberty. All right, so today we're going to make our own alloy, and it's going to look gold. You shall not spin this afterwards as your token of chemistry for yourself to keep forever. Okay, so our first part of our lab is going to be actually taking our pennies, which have a deep two different metals in them. We're going to put them in some zinc. This zinc is flammable zinc. It's powdered zinc. It's flammable, meaning don't put the zinc straight up in the fire. I'm going to go ahead and come around and put sodium hydroxide, NaOH. I'm going to put that on top of the zinc so that it doesn't react to the fire. Basically, any vigorous rubbing with the zinc, like with paper towel or so forth, would catch paper towel on fire. And I've had that happen one time in 6 years. I'm feeling pretty good about myself. Let's keep that record low. Okay. So other than that, that's just like about the safety concerns. The sodium hydroxide, NaOH, is a really strong base. So just like acids can burn you, bases can burn you. This is one of our more hazardous labs. So I know some of you are like, okay. So as we put our pennies into our zinc, we're going to put I have the zinc layer already down here. We're going to add our pennies on top. Then I'm going to add another layer of zinc on top to make like a little cookie, okay? So like an Oreo. And that's going to create ability for the alloy to form. So you have to read the lab really, really carefully. You can only bake about 4 pennies in a dish at a time. If you're not listening, then I'm not going to let you get in the lab. So you can only bake about 4 pennies in the dish at a time. That's about how big it is. Be patient because it will take about 10 to 15 minutes for it to finally finish its baking. So anything that touches the zinc will go into a 5-gallon bucket, which I have on the back lab station. No zinc down the sink. A little tiny bit that resides like on some like utensils, we'll wash it off carefully and then we'll try to put the rest on the sink, but not like a ton of zinc will go on the sink. And so especially your paper towels, if you have paper towels, you try to use minimal paper towels, but any paper towels that you touch with zinc goes in the 5-gallon bucket as well, because I don't want that in my trash can and like old trash can fire, okay? The longer it waits, the better, so just make sure that I come and see it so I can say, yeah, you're good, or no, you're not good. And then some people will have to babysit their Bunsen burner, or their container, okay? So here's our pennies, here's our Bunsen burner. Pennies start to boil, oh no, remove the Bunsen burner. Swing it back and forth, kind of rocking your Bunsen burner back and forth to heat it. Oh, it starts to boil, come out, okay? So you're basically just babysitting to make sure that the Bunsen burner doesn't allow the pennies to boil over. Other than that, I think you guys are good. So I have made lab groups. I just have a randomizer. You know how I like to kind of keep you mixed up sometimes. So look up. Let me make this a little smaller. Can you guys see your lab groups? I have 26 people in here. Please grab a sheet. Grab one of these sheets. And then, but when we get back to the lab, you're going to pull out your lab notebook first and maybe start reading the first part. This is your data sheet. Feel free to write all over it. Thank you. And then I'm going to ask for you guys to bring your pennies back to me at the fume hood because I have to clean them off with concentrated nitric acid. And I have to do that very quickly. So it has to be in an orderly fashion for us to kind of make the tackling pattern, but I'm ready if you are. You guys good? Let's roll. Goggles on. Please that's your lab station. Lab station 5. Lab station 5. The loading 5. Bring your pennies with you. Omar. Read your lab first. Read your lab first. Do not touch the zinc until we say so. Lab station 1 or 2 is right here where I'm standing. Lab station 3 is right here by Noah. Lab station 4. Thank you. This is lab station 10. Go to lab station. Go to Lauren's. Pull out
so as you're reading the lab, it will ask you to pull out some materials. Carefully pull out those materials. I actually need to turn the gas on as well, so go ahead and set your Bunsen burner up appropriately, but the gas is not on yet, so do not strike it. You can send one person to me with a paper towel and your pennies. One person with a paper towel and your pennies. One person to me with paper towels and your pennies. Next one, I would love you to start here. Thank you. Alright guys, you guys need to get everything out for the lab purposes. Read the lab. I'm seeing pennies. So let me put you Alright guys, I killed one penny. Give me a second to let this evacuate. This makes poisonous gas. Sorry guys, give me a second if you're waiting in line. If you want to see what a burning penny looks like, it's an EQ hose. It's like no one back. It makes a toxic gas being evacuated. So, while that was on, step right Please make sure you have 100% red with the bacteria gone. The gas is not on yet. Guys, you're actually not bouncing. That's why I just said put the data sheet in front of you. The data sheet does not say you pass. Alright guys, so at this point, listen up. At this point, your pennies are clean. You should have made your observation. Your pennies should be into your evaporation dish. Your Bunsen burner should be set up, ready to go, and turn the gas on. You guys can let me know. Let me know when you're ready. Alright, your pennies are in your evaporation dish. Your pennies are in your evaporation dish. Use your forceps and your crystal tongs. Forceps and crystal tongs. Check your drawers, guys. Raise your hand when you're ready for me. Okay, pause. You guys should know your equipment first of all. Forceps look like tweezers. Crystal tongs look like what? Tongs, are they rubberized? No, if you have rubberized ones, put them back because you will burn crap on the rubber. When you're ready, if you guys don't get started in like a minute, you're not going to be able to do the lab because it takes a while.
Wash and one. This is penny here versus penny here. Light brown to brown. I said thicker. Okay, these are structured. Make sure they push down. yeah, that's like a two-page bronze color.
Guys, the gas should not, the flame should not be on the bottom. The flame should be probably an inch away from the bottom. Turn your gas down. Because you don't want to boil it in the middle of the hot in the face.
What's the next step? Wait till she has the same color. It's the light, right? This is W on the right hand side. This is where the other one is. Cool.
Alright, you're babysitting. If you're ready, I'm coming.
Are we allowed to rest? Retouching her out. I hear you. You're on my next one. Guys, if you can't get your Bunsen burner lit, then have somebody else get it because I'm working right now. What's your name? Oh, great. That means not that part, the other part, the other part. Turn it down. Ooh, don't take your oxygen guys. Right here. Alright. Hey, what are we doing now? 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 I don't do this fire. So if it has yellow, that means it's too much. Yellow is too much oxygen.
So guys, you have a timer going. I want you to eat for at least 10 minutes, and then I have to see them. Go ahead and start trying to answer some of these post-analysis questions. Some of them don't require the results yet.
Washing and clothes. So if something has yours does not have that color. I think your gas is all the way on.
you like turn on that first. Some of the oxygen presents a little bit more. Bring your flame lower. A little less. Now, hey, you're watching, right? Somebody's.
Alright guys, you are watching somebody be babysitter, babysit and start answering those questions. We answer all of them.
Composition ratios. Sound good? I think it's because of money. It's gonna take money to get electrons to be paid on. And how strong you are, I guess. What else do you want to use? What happens to the code register? You don't know that's it. The advantages of preparing strength. Steel and bronze. Depends on how much money. What's it gonna cost? Hey, here's his bubbling.
Sandra.
Bradley, you gonna watch this?
Much, and as soon as I find out.
Alright, so you're gonna watch this. So you should be answering questions. Because if you keep bubbling like that, you can take it out. It's a very tedious way.
This is fire. I can burn. Kids can't necessarily burn me.
Don't bring it more up than it already is. Keep it flat. Right there. You can rock it. So this is point. So right. Boards over Seven to 10.
I said 10 to 15, you gotta listen earlier, because the longer the better.
Good job today, guys. Let me see your pennies. Hold them up proud. Are they gold?
Not really.
What are they? They're not gold.
They're golden.
They're just golden color. Yes. All right, bye, guys. There are no bells today.
8:37. Hey, make sure you grab the close reading on your way out. Grab it in your seven box.
There's no middle schools, you have to start there.
Make sure you guys grab your close reading. If you do not grab a close reading. Yeah, and I haven't printed anything yet. I got here late today for a meeting, but I did send you all. That's all I said.
The good thing that I've
Guys, there are no bells or class. There are no bells. Everybody grab the close reading. Jacob, do you have a close reading? Jacob, okay, good. Bradley, do you have a close
I
reading?
got a close reading.
Okay,
Bye, Sunbelt.
bye.
Yeah, like,